So this is the title of my talk, Frieze Patterns of Affine Type D. So this is a joint work with Emine Gunawan, Leah Bittman, Karin Baur, and Gordana Todorov. This was a part of WinArt, Women in Non-Commutative Geometry and Representation Theory workshop. So, okay, I'll first introduce you to the main object we will be talking about, Friezes. So the first definition is we can reference Conway and Coxeter. So these combinatorial objects are just arrays of positive integers. So we always start with an infinite row of zeros, an infinite row of ones, but stacked in this fashion. And then we write some numbers in the third row. So I'll call them row by row. But so, okay, after a row of zeros and ones, we put some positive integers. And we propagate below with respect to a rule, sometimes called determinant rule, sometimes called diamond rule, because what we are going to do, we are going to determine each entry in the next row by looking at all the other three. And the rule is, you can just think of it as a 2 by 2 matrix, and what you are doing is just taking a determinant. So you want determinant to be 1 for every 4 by 4 diamond. So if we do this computation here, so I use some colors. So 4 times 1 is 4, so we need 3 here. And what you do, you propagate it everywhere, 3, 1, so blah, blah. And then you complete this consecutively. After getting one row, of course, you will be able to determine the next one and next one. So for these numbers that I chose, miraculously, what happened is after finding this row, when we compute the next one, we again got a row of ones, and then we will have row of zeros here because it will be 1 times 1 minus 0. So we satisfy the determinant. So like if I take this thing and then move it everywhere, it should be the same row. So we should have this determinant of every diamond 1, and Coxey-Conway friezes are the ones where we actually close this frieze. It's called finite because it has finitely many rows. So we should be able to end with ones and zeros at the bottom. So usually when we talk about the width of the frieze, we only look at these sometimes called non-trivial rows, because these are always there. Okay. Of course, a basic non-example to Coxeter-Conway frieze could be just you take a row of zeros, a row of ones, and then you stack just twos in the third row, and then if you compute the determinant rule, you will get 3s here, 4 here, and blah, blah. So by just the induction argument, you can prove that this is an infinite frieze, namely it has infinitely many rows. It won't close with ones and zeros. So there are other, but it will still have integers, positive integers in each entry. Okay, so then the question is, how do we find these miraculous numbers that close up this combinatorics? And this is due to Conway and Coxeter. They show a bijection. So finite friezes of width n are in bijection with triangulations of n plus trigon. I'm sure this crowd love triangulations of polygons. So so you can see that this is a very cool combinatorics. And it's rich. Yes. Okay. So how does this work? And it's a beautiful combinatoric because it's also very simple. How does it work? Let's look at it. So this was the example. I give the definition. How do I get these miraculous numbers from a triangulation of a polygon? So we said the width means n plus trigon. So we had with 3 here, so I should have a hexagon. So I have 6 vertices. And by a triangulation, I mean, so I consider arcs between mark points. Here for a polygon, mark points are only on the boundary. So this is a triangulation. This is the maximal set of non-intersecting diagonals. That's a triangulation of a polygon, I consider. Okay, how do I get these numbers? Some of you may already even come up with it. So we have highlighted 6 integer because they will come from the 6 vertices of the polygon. And what I'm going to do, I'm going to simply count number of triangles at each vertices. So here I have 2, here I have 1, here I see 1, 2, 3, 4, here I see 1.
Yeah, okay.
And 2, 2. So this is how we get these numbers, 2, 2, 2, 1. And then we put them here periodically. So this is kind of this is called the Kuditi sequence. Kuditi sequence, because what we do basically, yeah, these are periodic. I take this sequence, I repeat it on the both side, and I propagate, and I get a Coxeter-Conway Frieze, a finite one. It will always close up with 1s and 0s. And these are combinatorially very interesting. They have very nice symmetries, glide symmetry, or many different symmetries that one can study. We'll be interested in these objects from different perspectives. Okay, that's how this bijection works. And for every triangulation of polygon, you can get a finite Frieze like that. Okay, this was just and then with respect to your background or what you like, you say, okay, these are beautiful objects, these associated to triangulations of polygon, and then this may connect you to Dinkin types. This is somehow studying triangulations of polygons are associated to type A combinatorics. And then we like Dinkin types, and then we can ask, okay, is this just specific to type A, or we can have these nice, beautiful objects for other types? For instance, if you're a Lie theorist, maybe you will go from thinking about Dinkin types, or a representation theorist or an algebraist. But you could also, if you're doing some surface combinatorics and cluster algebras, you can also take your view from the surfaces, right? So I did triangulations of polygon. Can I do triangulations of general surfaces? Or for instance, one option is I can consider an analysis that will probably be at the affine A combinatorics. We could consider type D combinatorics. This is a puncture, so we can allow putting mark points inside our surfaces and do triangulation. And then can we do these type of things? Even here, we can easily see if I do this triangulation for, let's say, type D, this surface punctured, the mark points on the surfaces are called punctures. I'll keep saying this probably. This has a boundary. We can do the same combinatorics. I can count the number of triangles at each vertex and then put it in this combinatorial gadget. And this was the non-example we gave. This will propagate infinitely many rows. So it seems these may give us interesting combinatorial objects like Friezes, or generalize the definition of Friezes from the point of view of Conway-Coxeter. Actually, type D actually is already studied. The Friezes associated to this type of setting, or type A affine A. I will talk about it a bit. And this is here, I put one example. How do we get actually these type of graphs from surfaces or surface triangulations? Is just for every diagonal, we put one vertex. So in the triangle, if I take a triangulation of annulus, where I have 3 mark points on this boundary, 2 mark points in the inner boundary, and then triangulate, I will have 1, 2, 3, 4, 5 diagonals, 5 vertices, and then I orient edges between any two diagonal respecting the orientation of the surface. If you fix it, you have your graph, directed graph. And yeah, so this is cool. Then you can go to algebras, you can go to combinatorics, you can do interesting stuff. Okay, yeah, and then this is type just and for one thing I wanted to mention, I put this not to forget, that's good. So for the triangulations of puncture surfaces, you may see these kind of weird looking triangles. That's actually a triangle because so what we do, we consider this is a folded triangle. It has one side here, second side, and the third one. So it has 3 sides, but it's folded. So for punctures, we may have this type of self-folded triangles in the triangulations. And we still, for the graph, we still get a graph. We have, for instance, 4 arcs. We will get 4 vertices. And now this is considered having arrows from both of them to this diagonal, and then you get a type D graph. Anyways, okay. So there is a beautiful way to go, an easy way to go from this triangulation of surfaces to directed graphs. Now we can generalize. We can say, okay, we can have infinite periodic Friezes. We just relax the condition of finite number of rows, but we still want periodicity and positive integers. So we will still want to have some periodic row and then propagating and getting only integers. So, and then actually there's a very beautiful result by Baur, Parson, and Shuggle. They say every periodic infinite Frieze comes from a triangulation of annulus. So if you, take the surface and triangulate it, in this case, we will have 2 boundaries. We will get 2 different Friezes, and they will be both infinite Friezes. And for every infinite Frieze, we can actually find a triangulation of an annulus. Yeah, so for instance, let's look at this example. So what I do the same thing, the same combinatoric as the polygon. For my outer boundary, I have 3 mark points, and I only count the number of triangles at each vertex and put it periodically in the first non-trivial row and then propagate. Here we get always positive integers. And for the inner part, we have 2 mark points, and then if I count the number of triangles at each vertices, I get this Coudity sequence. And then if I propagate, I get an infinite Frieze with positive integers. So, and then they realize a interesting thing about these 2 Friezes. So that leads us to this definition, growth of a Frieze. So for these infinite periodic Friezes, we have this Coudity sequence that we repeat. If we take this a Coudity sequence of length m, we define the growth. So these are infinite Friezes, so they grow fast, or probably exponential, or maybe differently. So there is this notion of growth coefficient, and it's looking at the difference between row m and row m minus 2, which is the row just above. We'll do an example Okay, maybe I'll mention this. And then what they prove actually, if you look at the growth of two infinite periodic Frieze coming from a triangulation of annulus, they have the same growth. So if you take two random infinite Frieze, their growth probably will not be the same. But if they're coming from the triangulation of an annulus, they will have the same growth. So for instance, let's look at this example. We had these two Friezes coming from the triangulation of this annulus. And what it says, so I look at the length of the Kuditi sequence. Here it's 3. So m is equal to 3. So I look at the row 3. So row 1. So I will, yeah, since these are the non-trivial rows, I'll actually, the convention is calling these starting row 1 from here, row 2, row 3. So I'll look at the differences between row 3 and row 1. Oops, not this. So these differences. So 10 minus 2 is 8, 10 minus 2 is 8, 12 minus 4 is 8, and so on. So here we have the growth coefficient, or simply let's call it growth, 8. Okay, let's look at this one. We have m is equal to 2. So I'll look at row 2 minus the row above it. So it's this one, 8. So we get the same growth. And this behavior propagates. If you look at the k, so if you take any multiple of m and k m minus 2, this difference will be again constant. So it will not be the same number. They will grow, and they grow. The growth satisfies a recurrence relation, which is quite popular, Chebyshev polynomials. So when you find the first one, the rest will be Chebyshev polynomials in this. Yes, so it's quite interesting. It's not a random growth. Okay. And then what we did, we asked, okay, when we get together with this group, we said, okay, can we do this for general surfaces or more general algebras and so on? Well, to understand why this is happening, like there should be a conceptual reason why this is happening. We looked at the next step was just considering tree boundary. If we have a surface with tree boundary, does this still, I can write 3 Friezes coming from this surface, and I can ask the same question, do they have the same growth? They will be infinite Friezes. But that's not true, because this is an simple example. If I write down the Kuditi sequences, the one for the outer boundary is for 3, and these are 1, 2, 3, 4, 5, 5, and 1, 2, 3, 4, 5, 6. So obviously, if I put these in this Frieze patterns, infinite Frieze patterns, they won't grow the same. So here, this is an example. So it fails if we have more than 2 boundary. But then we thought maybe there is maybe no example of the same growth, but then this example came up. Here we have always 5, I think. Yeah, 1, 2, 3, 4, 5. Yeah, so we can write 3 infinite Friezes from this triangulation, and then we get the same Kuditi sequence, so they grow the same. But yeah, there is no uniform behavior here. So we said, what should we do? We are mostly algebraist, so we said we should look at it more algebraically. So type A, D, and A tilde was done. So the next step is D tilde. And then the type E and E tilde. But the D tilde is more fun, affine. So this is the sum I call affine D. because well, I forgot what I was going to say, but oh yeah, it has the geometric model. Okay, that's what for type E. It's challenging to understand it combinatorially using surfaces. Okay, so what we did, we said we should do somehow have a notion of Friezes in this affine D type. This comes affine for affine D. We use triangulations of twice punctured disk. So here is an example. So this you can turn this self-folded triangles into these pairs, where you kind of remember that this is the loop around this puncture by putting a tag. So you can have this tagged arc. So, and then, yeah, this is somehow, it's the same thing how we get a graph out of surface, and then in this case, you will see it's this shape. But yeah, so this is a twice punctured disk. I have one boundary. Do I just get a one Frieze? So that's then the growth doesn't make sense. There's only one. But actually, what we did, we wanted to have a nice definition of a Frieze for the tilde. We looked at what were called Q representations. So these graphs are studied intensively in representation theory of, we call them Qers. And what we do, we put vector spaces at each vertices and linear map between them. This is just collection of vector spaces with linear maps, but they decompose nicely because our graph is nice. And there is actually, in this case, infinitely many representation that you can use to build any representation of this form, but they kind of get together nicely. So if I look at all possible, what we call indecomposable representations of these setting, we understand the representation category, even though we have infinitely many objects in this category. And interestingly, this representation category has this three what we call tubes. So these, for instance, this one will have n-2 representation, and they will have interesting maps and extensions between them. And then when you stack them together, they form these cyclic tubes. So, and then here we will have two tubes where there is two objects at the bottom, and then by considering extensions, we build other representations. So then we said, okay, these probably are our this should be our starting points to define Friezes. So these are representations over this graph. We have to output a number out of them from each representation. Roughly speaking, we do this by counting the number of submodules. We have to be careful. It's not as simple as this, but basically it rolls down to this counting submodules, and then how they look like in this big tube. The representations look very simple. Like I will have one-dimensional vector space here. If I don't put anything, that means 0. So this is like a representation where everywhere I have one-dimensional vector spaces and identities between them and blah, blah. So they will be the ones at the bottom of the first tube, T1, and then they will grow, so they will be other representations, but we can also understand them in terms of surface combinatorics. We know what is the corresponding arc on the surface for this representation. So we can turn this language into, after understanding the algebra and these numbers, we can actually turn all this computation into the combinatorics of surfaces. We understand each representation in terms of arcs on the surfaces, and it turns out for this T1, we will have arcs that skips one point on the boundary. So in this example, for instance, these are the candidates that will give you this integer number that you should take for a Frieze. And then the other tubes, they consist these representations, these two tubes, and then they turn out to be these two special arcs between the punctures. So this tube will have this arc with this one, which is tagged on both sides, and here you have kind of a nice symmetric part. So, and then, so as I said, there is different ways to actually compute the integer out of these arcs. So in this case, if we compute this, it's A, and these are all in terms of A, so they will always have a factor A, but since we have tagging, the extra numbers will pop up. It will be the valency of these punctures. So it's quite nice and natural, actually. And then what we proved, that if we write down, so we had this 3 tubes, or 3, you can think of them combinatorially, these arcs. And then here you will have, if I can even do this was AP, AQ. If you write the Frieze with this Coudity sequence, it was here APQ, and then this one is something big. So if you write these 3 different infinite Friezes with these Coudity sequences, their growth will be the same. So for twice punctured disk, for these 3 Frieze, we get this nice property. They have the same growth. And the growth also has a meaning in terms of the surface combinatorics. The value of this growth is really captured by this band around the 2 punctures. And then here an explicit example of a Frieze where for the outer boundary, we do always the same thing. We just count this, like I said, these arcs, but they are basically rolling down to counting number of triangles at vertices. And then we write for the outer boundary, it's 2 to 9. We propagate, we get this infinite Frieze, what will be the growth? It is, so length 3, 1, 2, 3, 23. Yeah, 23. And then here there will be, so the 2 of the same Frieze. And then the Coudity sequence is 5, 5. And this will be length 2. So I have these 23, 23, 23. So we get the two copies of the same Frieze because of the symmetry of the surface. And I think one example here, for instance, this is another triangulation of a twice punctured disk, and then we can obtain these 3 different Frieze. And if we look at the so it's again 4 to 2, the growth. So 1, 2, 3, then I will have 1, 2, 3. So these parts, yeah, 22. And then if I look at the other one here, it's 4, 6, 4, 6, 4, 6. So it's 22 again. So nice. And then, I mean, this is also, there isn't, so I picked up these like you already saw the symmetry, how these 2 small tubes behave, but you see it's like this is 24, 2 times 12 is 24. There's a nice kind of combinatoric here, not very complicated, but it matches with this big thing. I think maybe I'll stop here. Thank you so much.
All right. Thank you, Emine.
Yes.
Do we have some questions in the chat?
Yeah, so Nikita asks, is there a connection between the triangulation triangulations to indecomposable representations of cubes. So when we fix our, maybe I go to this simple case. So when we fix our triangulations, we write a graph, right, in the simple example, for instance. So for every diagonal, we put a vertex, and then you get this directed graph we call keyword, and then you write the path algebra. So if you list all the representations, the rep q, so each representation in the representation category will be an arc. So you can, for instance, simply say, if I write, like usually these things start with the projective modules or projective representations, and it propagates. So this, and then, yeah, so in this case, there will be finitely many indecomposable representation, and each one of them will correspond to an arc on the surface. So what about these initial diagonals? To get these initial diagonals, we have to expand this representation category with shifted projectives. So you can see these as shifted projectives, and all the rest will correspond to a indecomposable module. So arcs will be interpreted as indecomposable modules. Does that sound good?
Yeah,
Okay.
thank you.
Okay, and then
Are the
yeah.
Okay, are the squares in the Friezes the subgroups given okay squares? Oh, these diamonds. Okay. That's an interesting question. That's an interesting question. I don't have an answer right away, but I'll think about it. So I will go to the next one for the time constraints. Well, we can talk about it, because there is a nice generalization from SL2 to, these are sometimes also called SL2, yeah, determinant to SLK. So there is a connection, but I won't go into it now. Maybe we can talk later. Okay. The next question, is there a simple reason that all the entries in the Frieze are integers? Yes, because they are counting formula, coming from some counting formulas. So for instance, so for these numbers, as an algebraist, if I look at them as coming from representations, these numbers are the number of submodules. If I'm looking at that in terms of cluster algebras, yeah, if I use cluster algebra language, it's super easy. Cluster algebras are Laurent polynomials with positive, so that they are positive with positive coefficients. If you specialize your variables to 1, you get always positive integers. It's thanks to the positivity of the positivity property of cluster algebra. So these are somehow integers coming from counting formulas. Basically, that's kind of the simple idea, but you can look at it from many different perspectives. So that's the beauty and richness of the theory. Okay.
Okay, I think I have the terrible job as a chair.
Yes.
Unfortunately, but the good news is that we can all move to, well, first of all, let's thank Emine again. And I guess we can continue the discussion.